Hello everyone. Today I am going to show you a toolbox which is for analog communication to show some values of input signal and your output signal which you say and their power also. So here are the functions. Here are many functions. So I will describe them one by one. So at first look at this dashboard. If you have ever worked with real hardware test benches, you know that signals aren't static, they are always moving. Okay, not always, but maximum of the time they are moving. Okay, so today we are building an uh, interactive signal analysis and modulation toolbox in Python, completely upgraded with fluid like real-time snake oscilloscope. As you can see here, these are moving like this. Okay, so this is actually the oscilloscope animation. So that slides across your screen perfectly, even when you input values are completely still. Okay, as you see, the input values are still here, okay, like this. So the entire visual interface features a live rolling time domain scope, a dual spectrum analyzer, an automated digital telemetry readout, and an integrated machine learning classifier that targets and identifies your waveforms on the fly. Okay, so when I change the mouse, like to if I change it to I think like this, if I change it to the sawtooth, or you can say the square wave, and when I change it, sorry, okay, so this is looking like a saw here. Okay, so let's talk about the simple math trick that makes these graphs crawl like snakes. Just one second, let me shift it. So and how this signal, sorry, and how you can use this signal toolbox to visualize complex signal behavior. Okay, so now after that, so normally if you plot a static signal array in Python inside a loop, the graph freezes because the numbers don't change. Okay, so let me first show you the code here. Okay, so to create the smooth continuous crawling motion, our toolbox introduces a dynamic time phase offset. Every time our 50 millisecond refresh timer clocks in the script required increments a global phase variable. Uh, the 50 millisecond here you can see it's a 50. Because of this, it is 50 millisecond. Because of this, it changes. So when we calculate our waveforms, we feed this moving phase directly into the trigonometric sine functions. This tricks the coordinate system into constantly sliding the wave horizontally across the viewport for our custom mouse draw feature. The script physically shifts the underlying array index in a circle, forcing your custom sketches to crawl across the display flawlessly. Okay, so let me shift once again to the page. So right above our moving waveforms sits our dedicated digital telemetry panel. Okay, because this is an evaluation toolbox, it calculates vital electrical metrics on the fly. It keeps track of peak to peak voltage VPP or root mean square voltage VRMS and the wave's absolute power density signature in both raw watts and standard RF, you can say dBm. Okay, so watch telemetry changes when I flip our wave profile from a smooth sine wave to a square wave. Okay, just see here, just see the values are changing, the power here, the decibel, everything is changing. So let me once again keep it to the sine wave. Okay, so power significantly increases. You see when I shift to the square wave. The toolbox visually proves that square waves carry more total energetic area because they pack infinite odd harmonics into the same peak-to-peak boundaries. Okay, so uh, then now let's see how the toolbox behaves under heavy modulation workloads. If we choose standard modulation, standard AM, or you can say amplitude modulation, the oscilloscope shows a moving carrier. Okay, wave getting compressed by our message signal. Switch over to the spectrum analyzer tab. When you see, one second, and you will see the exact frequency layout, a massive power spike in the middle representing the carrier and two smaller peaks on the sides holding the information. So as you can see here like this. Okay, if we toggle the scheme over DSB-SC, over the DSB-SC double-sided suppressed carrier, you can say, look at that, the central carrier peak. Just one second. Now look at that, the toolbox visually validates that we are successfully suppressing that wasteful carrier to save transmission power. And if you swap over to FM, the waves on our scope bunch together and stretch out dynamically as the frequency modulates across the time. Okay, just one second. Let me change the frequency. See the magic. Okay. Uh, it the waves on our scope bunch together and stretch out dynamically as the frequency modulates across the time axis. Okay. So the ultimate benefit of this toolbox. One second. The ultimate benefit of this toolbox is that it runs entirely in software. There is absolutely no external hardware, wires or radio equipment required. The script is structured vertically using PYQT5 and PYQT graph, meaning it runs battery smoothly on almost any computer. Okay. So I have dropped full updated animation as you can see here. So if possible, I will be attaching everything important required in the description also. So if you like my video, please subscribe my channel and please give a like and please do a comment. Okay, so let me just before quitting the video, just let me show you the sound. Okay, so these are the sounds when you say. So let me go to oscilloscope.